CobotGear, interaction with collaborative robots using wearable optical motion capturing systems. This research was developed in the Intelligent Space Robotics and Virtual Reality Laboratory at the Skolkovo Institute of Science and Technology Skoltech. Problem statement. Demand for collaborative robots, because of their flexibility, safety, and productivity, is expected to increase sharply over the next few years, with sustained growth projected over the next decade. The global collaborative robots market will grow at 49.14% during the forecast period 2017 to 2025 according to Inkwood Research Report. Also, according to the Occupational Safety and Health Administration Incidents Report in the U.S., 37 robot accidents occurred between 1984 and 2013. For instance, in Germany, at the Volkswagen assembling factory, a contractor was setting up a robot when the robot grabbed and crushed him against a metal plate. At the same time, 4,000 workplace accidents were reported in 2013 alone. This means that robot-related issues represent a mere fraction of all workplace accidents. Still, one accident is too many. Many companies are using collaborative robots in their industrial lines. However, even the most advanced industries are not completely automated. For example, the final stages of aircraft and automobile assembling are still mostly manually operated, involving minimal use of automation. We propose to develop a framework, where the robots and people work together, increasing productivity and efficiency. The robot provides high load capacity and process repetitiveness, and human operator possesses the versatility and manual skills in dexterity activities. Here are 4 papers about safe human-robot interaction frameworks. In the first paper, a hybrid multi-camera is used to track the people. The cameras are located in an external fixed position. In the second paper, researchers located a camera in the end effector of the robot to track the environment. In the third paper, a novel device for safe physical human-robot interaction was presented. In the fourth paper, a motion capture system based on a set of cameras was applied to track the human position. During the literature review, we realized that most of the research for safe human-robot interaction is done using cameras. We wanted to prove that active optical technologies can be applied to solve this task, improving the efficiency and performance of the framework. We propose to develop a novel, safe human-robot interaction framework with 2 principal vital elements. First, to track the human position in a collaborative environment. Optical active motion capture devices don't have the disadvantages of cameras that can be occluded by the elements of the environment. Second, to design, simulate, and calibrate a collision avoidance algorithm for safe human-robot interaction. Environment perception. HTC Vive technology uses 2 base stations, lighthouses, as references. The tracker has 18 infrared sensors that receive the signal from base stations. The position of the device is determined by the time difference between the signals emitted by each base. This system has a low latency. However, it requires base stations and has glitches caused by reflective surfaces in the room. Therefore, HTC Vive is not suitable for industrial environments. We used this tracking technology for preliminary experiments of the algorithm. In the final experiment, we used antilatency device to track the user hand position. Antilatency uses a sensor fusion approach based on an optical active tracking system with real-time IMU correction. The advantages are scalability, only increasing the foam floor, the working area increase, and low latency of the measurement 2 kHz. Collision avoidance algorithm. We propose to discriminate between 2 types of obstacles. The obstacle type 1 is an imminent collision. To detect it, we measured the angle between the speed vector and the robot obstacle vector. If this angle is more significant than a parameter of calibration theta obstacle, this obstacle is type 1. Otherwise, it is type 2, non-imminent collision. The behavior tree decides what the algorithm should do during different cases. Position control was designed using the Lyapunov criteria to achieve the goal position. There are 2 avoidance controllers for the 2 types of obstacles. When the obstacle is dynamic, it can go inside of a critical area where the handling control method is deployed. Calibration algorithm experiments. The following two experiments were designed to analyze the proposed algorithm's behavior over different conditions. Each experiment considered only one algorithm factor, theta obstacle and activation threshold distance, as an independent variable. The robot moved between 2 points. The obstacle was located in the middle of the toe points. The video shows how the experiment was performed. The result for theta obstacle parameter of this experiment are shown in the figure on the left. It illustrates the reaction when the robot enters the avoidance zone using different values of theta obstacle parameter. The results for the activation threshold distance parameter of this experiment are shown in the figure on the right. It explains how the robot's trajectory was affected by the avoidance controller when the TCP enters the avoidance region. It is important to notice that, a small distance does not permit a proper evasion. On the other hand, a big distance generates an unnecessary delay and displacement of the robot. In this experiment, the algorithm has been implemented in a real-time human-robot interaction (HRI) application to evaluate the system performance. The user was located in front of the collaborative robot UR10 and was asked to wear the HTC tracker on the right hand, as shown in the video. The UR10 was continuously moving through 3 points, creating a virtual triangle. The input for the collision avoidance algorithm is the distance between the tracked human hand and the robot TCP. The experiment evaluates the algorithm's behavior when the robot and the operator have the same working area. The results of the first scenario are shown in the figures. The orange line shows the robot TCP trajectory without collision avoidance following the path between the positions A, B, and C. The green line shows the modified trajectory in the presence of the user's hand. The trajectories of the TCP illustrating the behavior of the proposed algorithm are presented in the right figure. The avoidance algorithm successfully avoided the human hand. After calibrating the controller and evaluating the system on a preliminary experiment, a new proposed task evaluates the algorithm when the user and the robot perform a collaborative activity in a shared working environment. This experiment resembles common activities in a warehouse. The task objective was to put objects, cubes and cylinders, from a rack into boxes. The user was located in front of the collaborative robot UR10 and was asked to wear the anti-latency 6DOF camera on the right hand. The robot took 2 cubes and 2 cylinders from the rack and moved them to a box. The human did the same activity with similar objects. The goal of the experiment is to evaluate the proposed algorithm under conditions of a high probability of collision. Here, you can see the results of the experiment. In Figure A, there is the trajectory of the robot without an operator in the working area. In Figure B, there is the trajectory of the robot with an operator in the working area. It is visible how the trajectory changes when the operator works. Our experiment proves that the collision avoidance algorithm prevents 7 collisions with the operator's hand. In this paper, a novel approach to safe human-robot collaboration using wearable optical motion capturing systems was introduced, applying 6DOF wearable optical mocap by Andy Latesse, with the advantage that the working can be easily arranged, and, if the camera is occluded, the hand position is available thanks to IMU odometry. Additionally, a novel collision avoidance method, based on APF for human-robot interaction (HRI), had been proposed. The algorithm is based on the identification and discrimination of 2 types of obstacles. Besides, it was validated how calibration parameters modify the response. In the experiments, the parameters were set as follows: activation threshold distance equal to 0.2 meters and theta obstacle equal to 45 degrees. During the experiments, the robot governed by the proposed algorithm did not collide with the user. The introduced technology allows the user to work and interact with a robot in the same environment safely. In future work, the velocity of the obstacle will be analyzed to improve the algorithm response time. Additional tacking points on the human limbs will be included in the system to enhance safety. The proposed technology will potentially allow humans to safely interact with multiple robots in cluttered environments, e.g., factories, the kitchen, living room, and restaurants. In one scenario, visitors of the shop could wear cameras, IR markers, or QR codes. Wearable cameras or robots would track hand positions to avoid the collision and to perform physical HRI tasks, e.g., taking the plate from the client. Thank you for your attention.